Hello dear students, the next topic of this lecture series based on the statistical physics is heat function. Heat function is also called enthalpy, which is represented by capital W. It is the sum of internal energy and product of pressure and volume. Mathematically, W is equal to E, which is internal energy, plus P, which is pressure, into V, which is volume. Since E, P and V are all state functions, therefore W is also a state function. Now what is state function? State functions are those functions which depend only on the initial and final positions irrespective of the path followed by them. Next is physical significance of heat function. Since we know that W is equal to E plus PV, which is mathematical definition of this heat function. Now change in heat function from position 1, let it be W1, to position 2, let it be W2, during any process is given by this small change is represented by delta. So delta W is equal to W2 minus W1. Now by definition, W2 is equal to E2 plus P2 into V2 minus W1 is equal to E1 plus P1 into V1. So on rearranging it, E2 minus E1 plus P2 into V2 minus P1 V1. So del W is equal to del E, which is small change in internal energy, plus del of product of pressure and volume. Let it be equation number 1. Now we know from the first law of thermodynamics that heat supply to the body is used to change the internal energy, which is del E, and work done or by the system, which is P del V. So W del Q is equal to WE plus P del V. This is first law of thermodynamics. So del E is equal to del E. Del E is equal to del Q minus P del V. Now putting this equation number 2 into 1. Putting this del E into equation number 1. So we will get del W is equal to del Q minus P del V, which is from equation number 2, plus del into PV. Now if the pressure of the process is kept constant, if P is constant, P1, P2 is equal to P, that is constant. Then del W is equal to del QP minus P del V plus P del V, because P is taken as a constant here, so it does not belong to any variation. So this may be cancelled out, similar and opposite terms. So del W is equal to del QP. Hence, what is the physical significance of this heat function and why is it called so? Because this del W represents the heat added to the system at constant pressure. Del W just represents the heat added to the system at constant pressure. That is why it is called heat function, because it is equal to heat, del Q. Now let's discuss about the total differential of heat function, that is dW. By definition, we know that W is equal to E plus PV. On differentiating it completely, dW is equal to dE plus, this is by parts, PdV and VdP. Then from first law of thermodynamics, dQ is equal to dE plus PdV. From second law of thermodynamics, dQ is equal to TdS. On combining both these laws, we get that TdS is equal to dE plus PdV. So dE is equal to TdS minus PdV. Now putting equation number 4 into 3. So this dE can be substituted here. So dW is equal to TdS minus PdV. This is dE and plus PdV plus VdP. Now On simplifying this, we can see that PdV minus and PdV plus will cancel out. So we are left with only two terms on right hand side, which are TdS plus VdP, which is the total differential of heat function W and represented by dW. This is total differential of W. Next is differentials of heat function. Since the total differential of heat function we have derived it, dW is equal to TdS plus VdP. You can remember it also. Now, on differentiating it with respect S by keeping pressure constant, so we will get that this curly W upon curly S at constant pressure is equal to temperature, because at constant pressure this term will become 0. Again, on differentiating it with respect to P at constant S, so we will get curly W upon curly P at constant entropy is equal to V. At constant entropy this term becomes 0. So these are two differentials of heat functions. One is at constant pressure and other is at constant entropy. So your heat function is function of your T and V. Now we will prove that heat function is conserved for thermally isolated body. We know that at constant pressure dW is equal to TdS plus VdP. So dW is equal to dQ. At constant pressure this term will become 0. And this TdS is equal to dQ from second law of thermodynamics. For a thermally isolated body, there is no loss or gain of heat content. There is no loss or gain of heat content. For a thermally isolated body, neither energy nor mass is exchanged with the surroundings by the system. So Q remains constant. Q remains always constant. So variation in this heat content is 0. Now if we see equation number 1 and 2, then this, because according to 1 dW is equal to dQ, and for a thermally isolated body this dQ comes out to be 0. So dW also comes out to be 0. This means W is also constant. Hence heat function is conserved. This W comes out to be constant for a thermally isolated system kept at constant pressure. It happens at a constant pressure. Now since the total differential of E dE is equal to TdS minus PdV, we know it. On dividing it with curly T and keeping V constant, then we will get curly E upon curly T at V constant. This comes out to be T into curly S upon curly T at V constant, at volume is kept constant, minus 0, because at constant volume this second term becomes 0. So this TdS is equal to curly Q. T curly S is equal to curly Q according to second law of thermodynamics. And this term we know that this variation of heat with temperature at constant volume, sorry, this is Q, is equal to Cv. Cv is specific heat at constant volume. Specific heat at constant volume. Also the total differential of W, we know that dW is equal to TdS plus VdP. Similarly, on dividing it with curly T and here keeping pressure constant. Here keeping pressure constant. So curly W upon curly T when P is constant comes out to be T into curly S upon curly T at constant pressure. At constant pressure this second term becomes 0. So TdS again is equal to curly Q. And this is called specific heat at constant pressure. So Cv is the specific heat at constant volume, which is equal to curly Q upon curly T at constant volume, and Cp is specific heat at constant volume, which is curly W upon curly T at constant pressure. So at constant pressure, the heat function W has the same properties as those of the energy at the constant temperature. They look like similar. Thanks for listening and watching.